For an example of the implicit function theorem for three variables, I'd like to consider the following hyperboloid of one sheet. We're going to find the partial derivative of z with respect to x and the partial derivative of z with respect to y for x squared minus y squared plus z squared minus 2z is equal to 4. Now technically this first step that I'm about to do is unnecessary because constants are not really going to have an impact. But for the sake of consistency with the implicit function theorem, we're going to get a 0 on one side. That way, this will now be referred to as capital F of x, y, and z. Now, according to the implicit function theorem, if I'm interested in finding the partial derivative of z with respect to x, this is going to be the negative partial derivative of f with respect to x divided by the partial derivative of f with respect to z. These derivatives shouldn't be too hard to take, so let's go ahead and take them. With respect to x, we have a 2x from the very first term, and every other term is being treated as a constant. In the denominator, the partial derivative of f with respect to z, the first two terms will be 0, the last term will be 0, but the two terms in the middle will become 2z minus 2. And of course, if you're interested, you could factor out a 2 from the top and the bottom and cancel those out. We'll call that negative x over z minus 1. For the partial derivative of z with respect to y, once again, according to the implicit function theorem, this will be the partial derivative of f with respect to y divided by the partial derivative of f with respect to z. Now we get to recycle the derivative of the denominator. So that's 2z minus 2. The partial derivative of f with respect to y, we have only one term that contains a y. That derivative will be negative 2y. We'll reduce this as well. We'll cancel the negative from the numerator with the negative in front of the fraction and reduce top and bottom by a factor of 2. That is the way our implicit function theorem works, and it is so much nicer than the technique of implicit differentiation.